What's the coldest possible thing in the universe? Not just a winter day or ice in your freezer, but the absolute, rock-bottom coldest temperature, absolute zero. At absolute zero, atoms and molecules nearly stop moving. Imagine everything holding perfectly still. This isn't just a number on a thermometer, it's a fundamental limit of nature. The search for absolute zero is a story of curiosity, clever experiments, and a quest to understand heat itself. Scientists didn't stumble on this idea overnight. It took generations of thinkers, each building on the last. They asked, can you keep cooling something forever, or is there a limit? These questions led to the birth of thermodynamics, the science of heat and energy. Every time you see steam or feel warmth, you're experiencing the principles these scientists uncovered. Their quest for the coldest cold revealed some of the hottest secrets of the universe. So, let's travel back in time and meet the minds who pieced together this chilling puzzle. From clunky thermometers to brilliant calculations, the story of absolute zero is a scientific adventure. Bundle up, we're heading to the coldest place imaginable. Before we talk about absolute zero, let's define temperature. For centuries, people just knew some things were hot, some cold. You could feel it, but not measure it. To move forward, science needed numbers for heat and cold. Enter the thermometer. Galileo's thermoscope, in 1596, was a start, showing warmer or cooler, but not exact values. Early thermometers were crude, but by the 1700s, scientists added scales, turning them into real measuring tools. Daniel Fahrenheit's mercury thermometer in 1724 set a new standard, using fixed points like freezing and body temperature. The Fahrenheit scale caught on, especially in the US. Then Anders Celsius in 1742 proposed a simpler scale, freezing and boiling points of water. Originally, Celsius set freezing at 100 and boiling at 0, backwards. After his death, the scale was flipped to what we use today. The Celsius scale became the scientific standard worldwide. Now, with reliable thermometers and scales, scientists could truly investigate temperature. Measuring heat and cold precisely opened the door to deeper discoveries. With these tools, the quest for the ultimate cold could really begin. The thermometer became the key to unlocking the secrets of temperature. From here, the story of absolute zero takes off. Let's see how simple questions about air and gases led to one of physics' most profound concepts. The first real clue to a lowest possible temperature came from French physicist Guillaume Amontons in the early 1700s. Working with air thermometers, Amontons noticed that as air cooled, its pressure dropped in a straight line with temperature. He wondered, if you keep cooling air, does the pressure eventually reach zero? He imagined extending the line down. At some point, the air would lose all its springiness. This, he reasoned, must be the ultimate cold, a true zero of temperature. Amontons predicted this point would be around -240 degrees Celsius. His instruments weren't perfect, the real value is closer to -273, but his idea was revolutionary. For the first time, experimental data suggested a limit to coldness. Absolute zero. Amontons planted the seed for a concept that would grow over the next 150 years. His work showed that temperature and pressure are deeply connected. The idea of a lowest possible temperature was now on the scientific map. The quest for absolute zero had its first real milestone. The journey was just beginning. Fast forward to the 1780s, France's golden age of ballooning. Jacques, a scientist and balloonist, noticed that heating gas made balloons expand and rise. Cooling made them shrink and fall. Curious, he experimented with different gases, heating them and measuring how much they expanded. He discovered all gases expanded by the same amount for the same temperature increase, a universal rule. Charles never published his findings, so his discovery was nearly lost to history. But his experiments revealed a simple, predictable relationship between temperature and gas volume. This insight would become crucial for understanding absolute zero. Charles's work showed that temperature affects all gases in the same way. The idea of a universal law for gases was born. Soon, another scientist would bring this hidden discovery to light. Enter Joseph-Louis Gay-Lussac, a meticulous French scientist and balloonist. He heard about Charles's experiments and decided to investigate further, measuring how much a fixed amount of gas expanded with heat. In 1802, Gay-Lussac published precise results. For every 1 degree, Celsius increase, a gas's volume increased by 1/273 of its volume at 0 degrees. This meant, in theory, cooling a gas by 273 degrees would shrink its volume to 0, pointing to a minimum temperature, minus 273 Celsius. This became known as Charles's Law. Gay-Lussac realized the law only worked while the substance stayed a gas, before it turned liquid or solid. Still, two different approaches, pressure and volume, both pointed to the same ultimate limit. The evidence for absolute zero was mounting. Scientists now had a powerful new tool for understanding temperature. The concept of an absolute minimum was becoming undeniable. The stage was set for a breakthrough. Now, cross the English Channel to the mid-1800s and meet William Thomson, later known as Lord Kelvin, a prodigy. Kelvin wanted a temperature scale not tied to water or any specific substance. In 1848, he proposed an absolute scale, based on energy and work, not just thermometer readings. Inspired by Sadi Carnot's work on heat engines, Kelvin realized temperature could be defined by energy alone. He combined this with data from Gay-Lussac and others, calculating absolute zero at minus 273.15 Celsius. This was the true bottom of the temperature scale, zero energy. Kelvin's insight was a huge leap. Temperature was now a measure of energy, not just a number. The idea of absolute zero became a scientific reality. Kelvin's work unified decades of discoveries. The foundation for modern thermodynamics was set. With absolute zero calculated, Lord Kelvin introduced a new temperature scale, starting at 0, with no negative numbers. The Kelvin scale's 0 point is absolute zero itself. Each degree Kelvin is the same size as a Celsius degree, making conversions easy. Just add 273.15. Water freezes at 273.15. Kelvin boils at 373.15. Kelvin and absolute zero is 0 Kelvin. No degree symbol, just Kelvin. The Kelvin scale quickly became the scientific standard. Why? Because its absolute 200 Kelvin has twice the energy of 100 Kelvin. That's not true for Celsius or Fahrenheit. Starting at true zero makes calculations in physics and chemistry much simpler. The Kelvin scale tied together the work of Amontons, Charles, Gay-Lussac, and Carnot. It gave science a universal language for temperature. The quest for the coldest cold had finally found its perfect scale. Absolute zero was now a cornerstone of science. So, we've found absolute zero, 0 Kelvin, the coldest possible temperature. But why does it matter if we can't actually reach it? The laws of thermodynamics say you can get close, but never quite touch 0 Kelvin. Still, the idea is crucial. As matter nears absolute zero, its properties change, in bizarre ways. Atoms nearly stop moving, and strange quantum effects emerge. Some materials become superconductors, conducting electricity with zero resistance. Others, like helium, become superfluids, flowing without friction, climbing walls, and defying gravity. Studying these phenomena helps us understand the quantum world. Cryogenics, the science of ultra-cold temperatures, relies on the Kelvin scale. It's vital for preserving biological samples, medical procedures, and space exploration. Infrared telescopes like the James Webb must be cooled to just a few dozen Kelvin to see the faintest galaxies. Absolute zero isn't just a number. It's a gateway to new technology and deeper understanding. The quest for cold has transformed science and our world. The impact of absolute zero reaches far beyond the lab. The quest for cold isn't over. Scientists today push ever closer to 0 Kelvin. Using lasers and magnetic fields, they cool atoms to billionths of a Kelvin above absolute zero. At these extremes, matter behaves in ways the pioneers never imagined. One breakthrough, the Bose-Einstein condensate, a new state of matter where atoms merge into a single superatom. This lets scientists study quantum effects on a visible scale. Ultra-cold research is driving new technologies, like quantum computers, machines that could revolutionize medicine, materials, and AI. All this depends on mastering the coldest environments possible. From simple questions about cold, we've unlocked a strange and wonderful quantum world. The story of absolute zero proves that even the most abstract ideas can change our lives. The chilly frontier of physics is still full of mysteries. Who knows what we'll discover next?